Hello everyone, welcome to Actuarial Path lesson on Poisson process and the gamma distribution. We start this lesson with an example or a couple examples of counting processes. Since the Poisson process is a counting process, then we follow that by formally defining what a Poisson process is. Then using the motivation of the Poisson process, we will derive the probability density function of the gamma distribution. And finally, we will lay out the relationship between the Poisson distribution, the Poisson process, the gamma distribution, and the exponential distribution. So what is a counting process? A counting process is a stochastic process that counts the number of arrivals of some specific event of interest. An example could be you could be interested in finding the distribution of the number of tweets sent out by the US president in any given day. Another example is, for instance, if you work for an insurance company as an actuary, you'll be very interested in the number of claims that your company is going to pay out in a given month or in a given year. And the last example I'm going to list here is you may be curious about the number of accidents at a busy intersection of the town or city you currently live in. And you'd like to get a data on that and come up with an expected value of variance or like a probabilistic view of it. Okay, let's build more on the first example, which is the number of tweets by the US president. On the day I recorded this video, actually on the day I wrote the material for this lesson, that is September 15, 2017, there were no tweets by the US president at midnight on time 0, which I'm considering time 0 of that day. My notation here is n of t is the number of tweets by the US president t hours into the day. You wake up early morning at 5 a.m. And then check your Twitter account. Well, you still have no tweets from the US president 5 hours into the day. However, at 6 a.m., you have 4 tweets. You check again after 1 hour. That would be 7 a.m., 7 hours into the day. Now there are 6 tweets. So you see what's happening here. So you can consider n of t as a random variable. And the process of counting is what we call a counting process. Therefore, a counting process is a stochastic process, which we denote by n of t, t at least equal to 0. It's a random process or stochastic process which satisfies these conditions. And one of the conditions is that the number of arrivals up until time t, on or before time t, is either 0, 1, 2, 3, and so on. Non-negative integers. And the second condition is that for time t2, which is later than t1, so we have this timeline, time 0, time t1, and time t2, so there could be events happening all along this timeline. The number of arrivals up until t2, which is later than t1, should be greater than or equal to the number of arrivals up until t1. Instead of counting the number of events in these discrete times, 5 o'clock, 6 o'clock, 7 o'clock, and so on, I could actually think of this process in terms of time until arrivals, or time between arrivals. And that's what we're going to do. And these are the actual times that tweets were sent out. The first 5 or so tweets arrived in fairly short amount of time between each other. Then after that, the inter-arrival times widen a little bit. Okay, let me draw this timeline again. Here we have time 0. And then the first tweet occurs at some point in that timeline, second tweet, and the third one, fourth one right after the third one, fifth one, and maybe there's a little gap between the two now, and then a slightly wider gap, and I can keep going. And please ignore my insensitivity to the distances between the times and the scale of this line. I want to define the time to the first arrival as x1, and the time between the first and the second arrival as x2, time between the second and third arrival as x3. So in general, I can I'll define x subscript j as the inter-arrival time between the j-1th event and the jth event. So that is the time between j-1th arrival and jth arrival. Instead of the inter-arrival times, you could also be interested in finding the distribution of time to the 10th, or time to the 20th, or time to the 5th arrival. So I'll define S1 as time to the first arrival, S2 as time to the second arrival, and S3 as time to the third arrival. And in general, S subscript n as time to the nth arrival, which is x1 plus x2 all the way up to x subscript n. Perhaps I should have defined the Poisson process slightly earlier on. But anyways, a Poisson process is a counting process, and based on these random variables that we defined, it satisfies the following conditions. First, the number of arrivals at time 0 is equal to 0. No arrivals at time 0. And the second condition is that the random variable n of t follows a Poisson distribution with the rate lambda t. So that means we know it's a probability mass function, and also the expected value, which is equal to lambda t, which is also the same as it's the variance. And the third condition is that the inter-arrival times x1, x2, and so on are IID random variables. That is, they are independent and identically distributed. The time to event random variables are therefore S1, which is equal to x1, s2, which is x1 plus x2 time to the second arrival, and Sn, which is time to the end arrival, is x1 plus x2 plus x3 and so on, all the way up to xn. Therefore, xn is time to the end arrival, and n takes values of 1, 2, 3, 4, and so on. Let us now find the distributions of these random variables. To keep things simple, let's start with x1, time to the first arrival. What is the distribution of x1? One way to do that is to find out the CDF, or the cumulative distribution function of x1, which is equal to the probability that x1 is less than or equal to little x. So that means what is the probability that the first arrival happens on or before time x. Let's draw this timeline, and we have time 0 right there and time x right at that point. And we want to find the probability that the first arrival happens on or before that time x. For completeness sake, I'm actually going to write that event, write it out. So that's the probability that the first arrival happens on or before time x. Let's think about a couple situations where this event may or may not be satisfied. If an arrival is after time x, if the first arrival is after time x, then the event that the first arrival is on or before time x is not satisfied. So that's the scenario that this event is not satisfied. Let's draw a timeline again and consider another scenario. If an event actually happens before time x, if the first arrival happens before time x, and regardless of how many arrivals happen after time x, our event is satisfied. Okay. Okay, let's look at one more example or one more situation where we have more than one arrival before time x. So 2 arrivals, or maybe even 3 arrivals before time x, and there could be further arrivals after time x. And in this situation, the event that the first arrival is on or before time x is satisfied. Therefore, the cumulative distribution function of time to the first arrival is equal to the probability that there's at least one arrival on or before time x. The number of arrivals up until time t, based on the definition of Poisson process we had, follows a Poisson distribution with a lambda t. And the probability mass function is equal to e to the negative lambda t to the power of n divided by n factorial. And n takes values of 0, 1, and so on. All right, we bring that down here, and we can write this the CDF of x1 as the probability that the number of arrivals up until time x is at least 1. Okay, we write it in terms of n, and that is equal to 1 minus n of x equals 0. It's easier to work with a complement. Okay, just utilizing the PMF of the Poisson distribution, we have 1 minus e to the negative lambda x to the power of 0 divided by 0 factorial. 0 factorial is 1. Lambda x to the power of 0 is 1 again. And therefore, we have the cumulative distribution function of time to the first arrival of a Poisson process equal to 1 minus e to the negative lambda x. And x takes values of 0 or more, and that's the non-negative real line. This quantity I'm circling is the cumulative distribution function of an exponential distribution with rate lambda. Therefore, we have shown that time to the first arrival of a Poisson process follows an exponential distribution with rate lambda. By the way, we do have an exponential distribution lesson, and check it out. All right, let's take this one step further. Let's try to find the distribution function of Sn, which is time to the nth arrival of a Poisson process. So Sn is equal to the sum k equals 1 to n of x subscript k. Like what we did before with x1, we'll seek to find the cumulative distribution function of Sn. Actually, we're going to go further and take the derivative of the cumulative distribution function to find the density of Sn. Let's start with the CDF. The CDF of Sn time to nth arrival is equal to the probability that Sn is less than or equal to little s. The nth arrival is on or before time s if there have been n or more arrivals on or before time s up until s. It could be n plus 1, n plus 2, or anything more than that. So this probability is equal to the probability that n of s is greater than or equal to n. And we know the Poisson distribution probability mass function, since n of s follows Poisson distribution, then we have this probability equal to the sum k equals n to infinity of e to the negative lambda s to the power of k divided by k factorial. Now let's find the probability density function of time to the nth arrival. And that is equal to the derivative with respect to s of the CDF of time to the nth arrival. Okay, when we take the derivative, we need to actually take the derivative of that expression inside the summation. Okay, the summation is indexed by k, and the limits of the summation do not depend on s. So we can actually move in the derivative inside the summation. So therefore, we have the sum, the derivative of e to the negative lambda s to the power of k divided by k factorial. Okay, so let's do this derivative. So we have the summation of k equals n to infinity of, we're going to utilize the product rule here. The first term, e to the negative lambda s, circling in black. And the second term, lambda s to the power of k, circling in red. By the product rule, I'm actually going to leave the first term, well, let me use black. I'm going to leave the first term as it is initially, so e to the negative lambda s, and then take the derivative of the second term, lambda s to the power of k. So that is lambda s, actually k times lambda s to the power of k minus 1. Need to also take the derivative of lambda s, so I have lambda plus the derivative of the first term, which is in black, that would be e to the negative lambda s. I need to take the derivative of negative lambda s again, so I have negative lambda times, now I will leave the second term as it is, lambda s to the power of k. Okay, so I have the denominator k factorial, which is common for both terms here. So I'm gonna leave them apart for now, since I plan to have two different summations for this derivation. Okay, so we have the sum k equals n to infinity of e to the negative lambda s, which is in both terms here, e to the negative lambda s. Notice there's a k in the numerator and a k factorial in the denominator. So we would have k minus 1 factorial in the denominator. Then lambda to the power of k minus 1 times lambda will give us lambda to the power of k. And we have s to the power of k minus 1. That's the first summation. And the second summation is sum k equals 0 to infinity. Well, we need to change the plus sign to negative sign because we have a negative lambda there. So therefore, this is e to the negative lambda s times lambda. Well, we have another lambda, so that will be lambda to the power of k plus 1, s to the power of k divided by k factorial. Okay, so let's take e to the negative lambda s, which is common to both summations. Outside here, e to the negative lambda s times, and the first summation is the sum k equals n to infinity of lambda k s to the power of k minus 1 divided by k minus 1 factorial. And we have taken e to the negative lambda s as a common multiplier, so we have minus the sum k equals n to infinity of lambda to the power of k plus 1 s to the power of k divided by k factorial. You notice that these two summations look very similar. So we have here lambda to the power of k, and we have lambda to the power of k plus 1, s to the power of k minus 1, and the index is incremented by 1 on the right side. We have k minus 1 factorial. The index of the summation k is again incremented by 1 on the right hand side. So this is telling us there's a lot of cancellation that can happen here, and let's do that. If we take this first summation and try to expand it, what do we get? So that's the sum k equals n to infinity of lambda to the power of k s to the power of k minus 1 divided by k minus 1 factorial. Now, if I plug in the first value, n, what do I have? I have lambda to the power of n, s to the power of n minus 1 divided by n minus 1 factorial. And then I have plus the sum k equals n plus 1, because I already used the first index equal to n to infinity of lambda to the power of k s to the power of k minus 1 divided by k minus 1 factorial. If I increment the index by 1 inside the summation, I need to subtract the limits by 1. So this is equal to lambda to the power of n, s to the power of n minus 1 factorial, plus the sum k equals n to infinity of, well, I took 1 away from the index, so I need to add it back in the index variable here. So lambda to the power of k plus 1, s to the power of k divided by k factorial. Now, this expression is exactly the same as that one. So these two cancel out. Okay, so therefore we have the probability density function of time to the nth arrival is equal to, now in place of this, I can use that expression, and this term basically cancels out with the other, exactly the same term. What's left over is e to the negative lambda s times that expression, lambda to the power of n, s to the n minus 1 divided by n minus 1 factorial. Okay. Rewriting this similar to how we typically write the probability density function of the gamma distribution. Yep, that's right. This is basically the gamma distribution probability density function. S to the power of n minus 1, e to the negative lambda s. And s takes values of greater than or equal to 0 in the real number line. In the next lesson, what we're going to do is actually show that gamma of n for integer n is equal to n minus 1 factorial. That's the gamma function. So we will introduce the gamma function in the next lesson. And this PDF that you see here is, if I replace the n minus 1 factorial by gamma of n, is the probability density function of the gamma distribution. One of the takeaways from this lesson is, therefore, the time to the nth arrival of a Poisson process follows a gamma distribution with parameters n and lambda, which we will define in the next lesson. Okay, before I close out, I want to give you one exercise, which is, if you remember, we found that the time to the first arrival followed an exponential distribution with rate lambda. And what we've just found now is the time to the nth arrival, which is x1 plus x2 plus all the way to xn, follows a gamma distribution with the parameters n and lambda. What I want you to show is that each of these x's, okay, are IID exponential lambda. Not only the first one, but all the others. All right, thanks.